Hello everybody and welcome to Boule Academy and this webinar that will be presented by Xinyu and Jeanette. My name is Marcus Gustafsson and I am the Customer Care Director here at Boule, and I hope you will have a very nice webinar today and that you have the opportunity to look at our Boule Academy and be patient. There will be even more information and material coming there during this year, so enjoy very much. Xinyu and Jeanette.
Thank you, Marcus, and good afternoon or good morning, depending on where you are. So I will give you some perspective of Medonic in a historical view. I will give you a short introduction to the system. I will touch upon the capillary sample application, as we call the MPA inlet functionality, and also the blood bank application and the walkaway functionality, the automation wheels. And then I will leave the word to my colleague Xinyu, who will walk you through Medonic M32 from a technical perspective. So, hematology is the medical discipline that covers studies and treatments of blood disorders. The science dates back as far as to the ancient Egypt and the practice of bloodletting. In the 1670s, the field gained a major breakthrough with the development of the high magnification microscope by the Dutch scientist Antony van Leeuwenhoek. In the 1950s, the first automated cell counters were introduced. Displayed here are the celloscope to the left, the first European cell counter, and the first Coulter counter Model A, developed by Wallace H. Coulter, the first American cell counter. These two cell counters were contemporary, however, based on simpler electronics and equipped with an integrated sample stand. The celloscope analyzer was both smaller and less costly than the Coulter counter Model A analyzer. The celloscope is also the predecessor of the Swealab analyzers. Medonic AB was founded in 1982 by Ingmar Berntsson and Bram Bottema, both with a long history and experience in hematology, in clinical chemistry, and also in blood banking engineering. Ingmar and Bram worked with cell counters at a Swedish company called Analysinstrument, Analytical Instruments in English, when they concluded that they could develop a cell counter of their own. The cell counters of that time used LED screens for reviewing of results. In 1985, Medonic launched its first own-developed cell counter, CA480, with a built-in display that also showed the histograms. Today, a complete blood count is one of the most frequently requested analyses by physicians to evaluate a patient's blood status. In addition to reporting the blood cell counts, an automated hematology analyzer also determines a range of other parameters, such as the hemoglobin content and parameters related to cell size, like these, and also calculated parameters like these. An automated analyzer therefore provides much more information than a manual microscopy. The blood cell count reflects the specific need for the different cell populations at a specific time point. The release of mature cells into circulation and their migration to various tissues are the results of organs communicating through the endocrine signaling system. And the presence of stem or progenitor cells in the bloodstream can be an indication of a bone marrow failure. However, immature cells can be difficult for a hematology analyzer to distinguish from normal cell populations. Blood smear analysis therefore remains an important diagnostic tool to determine abnormal cells. Typically, what you do is you let the analyzer do the actual count, which is then confirmed under the microscope. At the same time, you can look for immature or abnormal cells So a blood smear analysis is often used to follow up results flagged as abnormal from the automated count on the hematology analyzer. A complete blood count typically covers normal cell counts and parameters related to the red cell and platelet volumes, calculated parameters, and hemoglobin. As part of the blood count, a white cell differential is often conducted. In normal blood, about 60% of the cells are neutrophils. Neutrophils help fight bacteria and fungi, and the high count indicates a bacterial infection. Lymphocytes, accounting for about 30% of all white cells, help fight viruses. A high lymphocyte count can therefore be an indication of a virus infection. The last 10% comprises monocytes, eosinophils, and basophils. These cells are typically associated with allergies or parasite infections. A high number of monocytes, for example, can indicate a chronic inflammatory disease or a bacterial infection, whereas a high eosinophil counts give an indication of asthma, an allergic reaction, or a parasite infection. A high number of basophils is typically associated with inflammatory reactions, especially those causing allergic symptoms. Hematology analyzers are divided into 3-part systems and 5-part systems, differing in the white cell differential. Although this difference, that is the parameters marked in blue here, the rest of the basic hematology parameters are pretty much the same. A 3-part instrument differentiates white blood cells into the lymphocytes, the granulocytes, which mainly constitute the neutrophils, and mid cells, mainly including monocytes. A 3-part instrument will therefore answer the question of a viral infection or a bacterial infection that can be treated with antibiotics. It will also give you an indication of anemia or blood clotting problems. In addition, a high number of white cells can be an indication of certain forms of cancers, such as leukemia or lymphoma. A 5-part instrument, on the other hand, will provide more detailed information on conditions such as allergies and parasite infections. For most cases, the same decisions can be made with the 3-part analyzer as with a 5-part analyzer. And guidelines dictate that abnormal samples must anyway, regardless of instrument type, undergo manual examination by microscopy. Beyond this, a 3-part instrument can provide cost benefits in that these instruments are often cheaper and require fewer reagents. A 3-part instrument is also based on robust and well-proven impedance technology. These instruments typically require less maintenance, and as they only use impedance, these instruments are generally less complex, which is also reflected in the quality control with fewer parameters to monitor. So, a short introduction to the M32 analyzer. In 1998, Medonic was acquired by Boule Diagnostics, and in 2005, Medonic M-series 3-part analyzers were launched. As the next product generation, the M32 system was introduced in 2014. And in 2018, the Medonic product portfolio was expanded with the Medonic M51 5-part hematology analyzer. Medonic M32 provides the following: reporting of a complete blood count from a low sample volume enabled by the MPA module that supports capillary sample analysis directly from a fingerstick. Measurement accuracy enabled by the shear valve which has a closed design to minimize the risk of dust particles entering or salt buildup that might cause leakage. And walk-away automation that liberates time for other tasks in the lab, enabled by the automation wheels with a design that provides constant mixing of queued samples, which is especially important for samples with a high erythrocyte sedimentation rate. The system is available in 4 models that fit various clinical needs. All models include the closed shear valve. Standard, cap, and sampler models are all equipped with MPA module. The cap and sampler models are also equipped with a cap piercing device for sample aspiration from closed tubes to protect the operator from possibly infectious samples. And the sampler model provides a walk-away solution for 20 samples. Both the standard and sampler models have built-in mixers. One competitive advantage with Medonic M32 is that the system is tailored to the smaller laboratory by design. Instead of incorporating technologies and methods initially intended for the larger laboratory, Medonic M32 is purpose-built for the decentralized testing, with a capillary sample inlet that allows close monitoring of patients and the space-saving automation wheels. RFID-locked reagents not only secures the very important after-sales, but also the use of designated reagents to ensure analytical quality and performance of the system. Medonic M32 provides maximized amount of information with minimal number of reagents, clear system messages that guide the operator, special functionalities such as the extended platelet count, which has proven to be important, for example, for infectious disease that affects the platelets, such as, for example, dengue fever. Medonic M32 puts measurement reliability before cost. Very syringe-based aspiration method is cheaper, but can be sensitive to variable pressure conditions. The more costly shear valve technology cuts an exact sample volume each time, independent of ambient pressure conditions. Additionally, the analyzer requires very little maintenance, which can be a costly feature, for example, for 5-part analyzers. Medonic M32 is not one size fits all. Instead, the system supports multiple aspiration methods, is available with the multiple models to fit the specific need of a specific laboratory, and supports multiple sample types. So to the capillary sample application. Typically, arterial blood is used for determination of blood gases, while venous blood is recommended for laboratory testing. Accordingly, laboratory reference values are commonly set using venous blood samples. However, there are circumstances where capillary blood can be preferred. For example, capillary blood sampling can be an option for patients that are hard to puncture, such as elderly. As a finger stick is often easier on the patient, capillary sampling is typically also used in pediatrics. Also, for certain conditions that require frequent blood testing, capillary blood sampling can be preferred over venous blood. For example, in cases of leukemia or infectious diseases such as dengue fever or even the new coronavirus infection, close monitoring of the patient's blood status might be required. However, the relevance of using capillary blood in diagnostic testing is sometimes debated. In addition to differences in content between capillary and venous blood, improper preparation and blood collection procedures can also cause discrepancies between capillary and venous blood values. In hematology, for example, the tendency of the platelets to clump or adhere to tissue and to the walls of the capillary sampling tube can also affect the test results. Consequently, the platelet count can be 5 to 10% lower in capillary blood, and if platelet clumping occurs, the lymphocyte count can be falsely elevated. It is therefore important to follow general guidelines for capillary blood sample collection to obtain reliable results. The sampling procedure should ensure a good blood flow. A deep and firm puncture allows for free-flowing drops of blood. To increase the blood flow, the site for puncture can be warmed for 3 to 5 minutes before disinfection and puncture of the skin. To minimize interstitial or intracellular fluids in the sample, the first drop of blood should be wiped off with a clean tissue. The sample should be analyzed directly after collection and for optimal results, no longer than 10 minutes from collection. This procedure shown here is adapted from the Clinical and Laboratory Standards Institute. Following these instructions, this is what a comparison between venous blood samples using the open tube inlets and capillary blood using the MPA inlet can look like. As you can see, the mode-to-mode comparison also for platelets in capillary samples passed in our testing, although somewhat lower than in venous blood. This table shows capillary samples analyzed using the open tube inlet as well as the MPA inlet. Also here, all parameters passed based on set specification limits. So I will now show you a video of the MPA inlet. So to the blood bank application. For certain acute or chronic health conditions that affect the blood cells, a blood transfusion can be the only therapy available. However, such an intervention can be associated with risks, for example, of adverse reactions such as fever as response to the transfused cells or an infection transfer to the recipient. Blood banks and transfusion centers therefore undertake certain measures to ensure transfusion safety. And hematology testing constitutes an important part of this, for example, in pre and post transfusion assessments, as well as in quality monitoring of the blood products. A blood transfusion provides the patient with required blood components, for example, in the event of an acute blood loss. Red blood cells can be given when the hemoglobin is low, for example, due to a disease, a bleeding caused by an injury or during surgery, or in case of anemia. Platelets can be given to treat patients that are either low in platelets or show poor platelet function. Whole blood is also sometimes given, for example, in case of a massive bleeding, in exchange transfusions, or when people donate blood to themselves. Whole blood to be used in transfusion from a donor to a recipient is often depleted from white blood cells when they are not considered to provide any benefits, but rather constitute a risk of transferring bacteria or viruses to the recipient. With a panel of regular voluntary blood donors, which are screened for infectious agents and with good manufacturing practices for the blood products, however, the risk of blood-borne infections can be minimized. For blood transfusion safety, it is also recommended that blood banks have in place an effective quality system that includes standardized procedures and good manufacturing practices. and to undertake specific measures to ensure correct labeling, storage, and transportation of all the blood products. The MPA method makes the analyzer well suited for use in assessment of both donors and the recipient. In a study performed at Bloodworks Northwest Donor Center in Seattle, USA, the MPA and open tube sampling methods of Medonic M32 were compared in assessments of female and male adult donors. Sample analysis showed no male donors outside of limits with either the open tube or MPA method. For female donors, 3 samples were observed outside of limit with the open tube method, of which 2 were observed outside of limits also with the MPA method. The 3rd sample was shown to be outside of limit with the open tube was observed close to limit with the MPA method. These results indicate good agreement between the MPA and open tube sampling methods. It shall be noted, however, that operator skills play an important role in analysis of capillary blood. Hematology testing is commonly used also in quality monitoring of the blood products. For example, platelet concentrates are typically assessed for residual leukocytes, and red blood cell products are additionally assessed for hemoglobin and hematocrit values. The blood bank application resides in the Medonic M32 analyzers as a special analysis profile. The factory default blood bank profile is named PLTC, as in platelet concentrate. The profile is pre-installed in the instrument and can be activated by the service technician upon delivery of the system. When using PLTC profile, the results will be presented with fewer parameters. The platelet linearity in the PLTC profile ranges up to 5,000 billion cells per liter, as compared with up to 1,800 billion cells per liter in the normal blood profile. Red cell concentrates are analyzed in a normal blood profile with a linearity range of up to 7 trillion cells per liter. So, walkaway functionality. The Medonic M32 sampler model is intended for high throughput laboratories, for example, as a backup instrument in larger hospital laboratories. The sampler model is also used in smaller hospital laboratories that are in no need for more detailed information that you get from a 5-part system. So with this, I will leave the word over to my colleague, Xinyu. Thank you.
Thank you, Annette, for the nice product presentation. So you see, M32 has multiple models and also some specific feature to suit different user need. So now I will continue to give you an introduction of how the instrument is designed and what the technology used to achieve these functions. M32, it is a 3-part hematology analyzer built on a proven technology, impedance measurement. In principle, it is a particle which passing an aperture with a constant current loading, and the size can be measured by the voltage diffraction when the particle passing the aperture. And to achieve high precision measurement, the system should let the particle moving through the aperture in an even flow. So the laminar flow through aperture will ensure there is no artifact, for example, coincidence event, and the instrument and the solution in M32 is by a mild constant pressure through the closed chamber and press the diluted cell through the aperture. And the system is designed to make this flow mild and even. And we will look later in the hardware build-up how this is achieved. All hematology analyzers, when using reagent and impedance technology, the task is quite common. That is to measure a precise volume of whole blood, dilute this blood into a highly diluted blood volume in the measuring chamber, and high dilution ratio gave advantage for precise measurement. M32 use two-step dilution. The first step, it is common for all the parameters. So this is 1 to 200 dilution into the mixed chamber. The second dilution is separate. The diluted blood is again measured for a precise volume and then diluted one more time for 1 to 200 into the RBC chamber for measuring RBC and the platelet. So from the whole blood, the final dilution for the RBC platelet is 1 to 40,000. So this is a very high dilution ratio. The other passage after the first dilution for the WBC, it is another 1-to-1 dilution. So the final ratio is 1 to 400. It is less dilution ratio, but it's enough to measure precisely for the WBC cells. Since the ratio of cell number in normal human blood for the WBC and RBC is about 1 to 1,000. So such difference for dilution can ensure both RBC and WBC can give precise measurement. And also here we already see when we deal with troubleshooting, for example, instability of a result, we can use this simple diagram to analyze which parameter is correlate with which one. And then we can deduct if it is problem with the first dilution or with the second dilution steps. So let's see the hardware. In this schematic drawing, you see the shear valve, which take precise volume measure for the whole blood, and then make a dilution into the mixing beaker. So here it is the first dilution for all the parameters, preparing for second dilution. And second dilution, the diluted blood also pass shear valve, another channel inside the shear valve, to measure also a precision volume for the RBC and platelet measurement. While inside the instrument, there will be a fixed length tubing with exact volume to measure the volume of first diluted blood preparing for WBC second dilution. So here we can see RBC and WBC chamber finally get final diluted blood ready for measurement. And the measurement is performed by an even pressure from a slave pump. So it is a passive pump to ensure the pressure applied inside a closed chamber is constant and mild to make a laminar flow of cells through the aperture. Here, the total number of cells is measured by the size of the voltage diffraction through the particle, by the particle through the aperture, and also the shape of the curve. Algorithms can determine the cell volume, and by this, instrument can make a plot called histogram to show the distribution of different size of cell in the blood passing through the measuring aperture. So this is the hardware build-up of the instrument in a very schematic drawing. Already here we can see, in case there will be a problem, we can go in narrow down to specific part of the instrument for troubleshooting. Some of us may have long experience with the IVD instrument. Some maybe just enter the hematology field for support the end user with various questions and problems. And actually this schematic drawing of M32 can provide us a structured analytical tool to narrow down the trouble. So many times, if the problem is simple, maybe we can solve the problem just by ocular inspection to see some signs of leakage or stop. But for complex questions, especially result questions, either it is instability, incorrect, we need to focus on these structural build-up of instrument, try to narrow down which part is related to the parameters involved with the measurement. We put quite big emphasis on the MPA inlet, since it is both convenient and also unique for Boule three-part instrument. And here you can see the open tube inlet measuring the whole blood volume by shear valve from a sampling tube, either from the open tube or from the closed tubing models as a cap-piercer model or the walk-away sampling model. And instrument also equipped with the MPA module, which user can sample directly from fingertip or from a smaller sample tube to make measuring directly inside the instrument. And here is the microtube instead of shear valve to take the whole blood volume. And as Annette mentioned and also emphasized on this very good feature, but also depending on the correct operation of the user. to make sure only the microcapillary tube contains blood. No air bubble inside, no excessive blood on the outside wall. So that means the operator should check if there is any air bubble inside the tube and wipe out, clean away with a tissue paper the excessive blood from outside. And in this way, the precision of the MPA inlet can provide a very reliable result. And we have sometimes questions from the user challenging the difference between the open tube and the MPA result, and how we can check if the results are reliable. We can also use some other materials like a control blood to verify, and this we will also talk very shortly. This seminar is an introductory seminar. We will not go into detail about each menu functions, since the menu system, the menu structure is well written. So you can see in the user menu, and there is a very clear overview of how the menu looks like, how each level of the menu are connected. So in case you don't have an instrument in front of you to support, to do tech support, you can either have a paper format user menu, or you can download a PDF version from our support site. And the M32 system, it is an upgrade from a previous M-series instrument. The CPU board are completely different. Database structure is different, and also the screen representation of the result and the menu structure are also different. But the hardware build-up inside the instrument are quite similar. The pneumatical handling, dilution steps, and the major measuring parts are the same. M32 is not only an analyzer, it is a hematology system with a total quality concept. That means analyzer, reagent, control and calibrator blood all contribute to a reliable measurement. And also all hematology analyzer based on reagent and impedance measuring principle due to the handling of whole blood, which contains various organic and salt substance. The cleaning is necessary. Even the M32 require quite minimal maintenance. So Boule cleaning kit, which contains 3 components, hypochlorite 2%, detergent cleaner, and enzymatic cleaner in the Boule cleaning kit. It is a very useful tool for end user to keep the instrument in a good working conditions. Analyzer coming to market in 2 formats. not hardware, but software configuration. The barcode reagent input and the RFID input type of instrument software. They have a different article number. For the previous instrument, it is possible to convert from a barcode reagent input type into an RFID reagent input type, not the opposite. So it is possible to order a RFID conversion kit to upgrade the barcode reagent input type instrument into a RFID type. And then reagent also coming into two format with a RFID tag attached or with the barcode type. So this gave a challenge. If on your market you have user using different type, so you need to plan for logistic of the reagent stock to supply the end user, since these two type of reagent input are not compatible. Control and calibrator blood are a very important component of the total quality system. Calibrator is designed, designated to calibrate the instrument, and the control blood is used to verify the instrument result. We will talk shortly the difference between them and the case when each one should be used. And next, we will go through some issues or highlight some point for the M32 operation. In many customer sites, the installation of a new M32 is either by a product specialist or by a service personnel. So during installation, the person who do the installation will ensure that the instrument pass the requirement for performance and also take time to do end user training, both for some specific features for operation like the MPA, but also for simple maintenance like running cleaning of the component of a Boule cleaning kit. The background check is to make sure the instrument can start to fit, since after transport process or long time storage, there could be built up of contamination inside the tubing system. And when starting up the instrument, all the particles should be rinsed out to reach the acceptable background level. And then after the background is acceptable, control blood verification is to see the instrument performance is good. And in certain cases, if the instrument is not precise calibration is needed. Instruments also provide many convenient functions for making different blood analysis profiles to suit demographic groups or some specific purpose. For example, for the blood bank application, for measuring some special body fluid. Instruments also provide password-protected login to give access for different levels of the instrument. And this is, for some regions, it is also a requirement. And instrument can also conveniently make often used functions in a quick menu. Has onboard QC functions to long-term monitor the instrument performance. Before we go in deeper of the operation and the menu system, I'd like to share with you two common but important concepts for all measurement instrument, and especially to fit for the hematology analyzer: accuracy and precision. I believe most all of you know these two concepts, but I like to emphasize so to make all of us clear the difference between them, and in practice, how the symptom of different problems is masked by either in these two concepts, and what the action needed in case one or the other is not good. Here we see 4 cases. Let's start from this quite bad case. A multiple measurement, both spread out, and also even make an average of all the measurement. The true result is still not in the target. This is the case of a bad accuracy and a bad precision. And here we have okay precision, okay accuracy, since the average of multiple repeated measurement can get close to the true value, but the precision is not good. Here we have a good precision, but accuracy is not good. And in this case, we can bring this measurement to the target by a calibration of the measuring instrument. So into this case, on the instrument user menu, we have the instrument performance specification specify the precision which the instrument is designed. So in case we get the instrument precision deteriorated outside the specification range, that is an instrument problem. Either it is due to the pre-analytical factors, blood sample handling, old sample, anticoagulant problem, or due to the precision measurement of volume in the instrument. So in this case, we need to solve the precision problem before we can check the accuracy. And if the precision is good and accuracy is not, then we come to the scenario that instrument need calibration. Here comes calibrator blood into play. Calibrator blood, it is a high accurate blood with a shorter shelf life and shorter open well viability. So a calibrator blood is produced 8 batch per year to make it is the analysis result is accurate as the assay sheet. So when the instrument need calibration, the control blood is needed. To check if the instrument gave good precision, end user need to use control blood. Control blood is produced 4 batch per year with a 3 months shelf life and longer open well viability. It is to check the performance of instrument, and in case the result is unstable, then user can run multiple time control blood, and then in the instrument menu to choose this sample to do a statistic either on the instrument menu or can use an Excel sheet to calculate the precision level of this measurement. And in case the precision is not good, then to troubleshoot the reason. Since now we use control blood, we are more, we can exclude the sample issue, since a control blood in inside of fresh control blood can give a stable result in its viable life period. So control blood is a very useful material when end user have questions regarding the result. Let's have a look of the instrument menu system. On the left side, we have 4 major functions. These folders: play, result, short function, and main menu, contains the access point for different function. The run folder is where the blood sample is analyzed. And here we have different profile showing up for user to choose. And user can also define their own new profiles to suit for different either demographic groups or some special samples. And here we have also sample ID, ID2, which it is customizable. In case the user don't need, they can inactivate and not shown in here. After an analysis, instruments show numerical results, and with 2 representation. The scale representation is good for clinicians. Here is very visible to see which parameter is out of the normal range of that specific profile. And with the graph presentation, which is very useful for troubleshoot and for engineers. Here we can see the histogram of the blood population distribution. And when user has question regarding the accuracy or precision, stability of result, we like to see the graph of control blood and patient's sample. And here we can see, for example, if the distribution of WBC curve is left or right shift, then probably we can solve the result of diff problem by adjust the gain of the WBC channel. The result folder, we get access to see result in different time period, and also with search function, we can choose a subset of result and either export, print, or to do statistics to check the precision and see how the precision of the instrument like is shown here. Next, in the quick function folder, by default, these functions are often used. Prime cycle is probably the most used function in case any fluidic system problem appears. End user is asked to do a prime cycle. Since some part of tubing, the liquid is not exchanged between each cycle. So in case an air bubble get into such tubing segment, only a prime cycle can reset the total fluidic status. The quick function menu is customizable. So after login in the service level, we can add other functions into the quick function menu to get quicker access. And then in the main menu, maintenance, it is most to do the fluidic system handling. Mostly it is for cleaning, to run Boule cleaning kit. Setup give access to various settings and instrument information is also can be shown. QC menu, it is for the long-term monitor of instrument performance by the XB and LG, and also for control blood input. Calibration has also two levels of calibration: guided, which can be performed by the end user, and advanced, which is usually done by the service engineer. System info contains a page which we can see the instrument serial number, software version, and also get a technical parameter information, which we will see quickly. Service manual provide adjustment of instrument gain for RBC, WBC, and also doing individual component test. So let's go through some points for these menus. The setup menu. Printer setup. It is to add a printer, to choose the printer type. M32, it is a Linux-based specialized system. It's not possible to add printer driver after. So that means the compatible printer connected directly to the instrument is limited. So in this case, the HP PCL5 compatible printer can be connected, and some printer may be difficult to find on your market. In that case, there is a function to export result as a PDF report to a USB stick, and then user can use a printer connected to a computer to print. In case it is too difficult to find a direct connected printer to the instrument. Communication set the setting for the LIS computer to receive result from an instrument in XML or HL7 format, both by serial connection, USB cable, or by an Ethernet connection. And there, if it is sent by the Ethernet via the HL7, the user need to set the IP address to the computer and also the port to send the result. Some instrument which switch off often. For example, in some place, the power supply is not stable during the night. Instrument need to be switched off, and instrument can give a RTC error after a period of time. That is due to the backup battery drain off. So in case user get RTC error, they need to check the backup battery voltage. And another case can be the user don't set date and time under the service login. At user level, set the date and time save could not be held after a restart. So this can also give RTC error. Regional setup, it is for the parameter name in the local language and also for the instrument manual language. And also here, the profiles for different profile, the parameter normal range can be changed and new profile can be created. These are some questions often raised by the end user. And here with the advanced setup, the blood detector, which locates inside the shear valve, we can set a time to bypass the blood detector for aspirate the whole blood. So in that case, if end user need runs special body fluid, which has low conductance, which the blood sensor cannot sense the sample, then the end user can set a fixed time for aspiration the sample inside the shear valve channel. But exactly time is depending the viscosity of the fluid and need to be checked by trial and error to get a correct transfer time. High altitude is actually change the WBC chamber feeding level. And even instrument can tolerate quite big variation of altitude. User can use this setting to solve some problem with HGB measurement. Some HGB flag are related to the WBC chamber filling levels, and this can be used as a troubleshooting tool to check if the HGB problem is due to the filling level. In the service setup, provide a function for the memory setting, which the raw data can be saved, and that is mainly for troubleshooting to get a more low-level data. And here, backup, import, and setting can be used to save a setting from one instrument and then to make a group of other instruments have a similar setting for large labs or a chain of clinics. Create USB demo is to make a USB demo disk and on another instrument to start a demo without running reagent on that instrument. In the maintenance menu, have 2 pages. The first is to run fill empty of reagent, to do prime, to get into standby, and to go to the power down procedure. We will specify this power down procedure because there are problems related. We will see shortly. The difference between the maintenance cleaning, clean fill, clean empty, and with fill and empty, it is the reagent detector, the level detector. When run in the maintenance cleaning menu, instrument will not taking into account of the level detector signal. So instrument will follow the user order to do fill or empty. And also the reagent cycle counter is not affected. So when the user run Boule cleaning kit, they must run under the cleaning menu. Otherwise, if they run in the cycle menu, the instrument cycle counter is reduced. So that will create maybe the cycle number down to 0, and still there are quite a lot of reagents in the container. In the calibration menu, after software version 2.3, instrument provide a guided calibration, and their end user can do this guided calibration, just follow the on-screen instruction. The advanced calibration is used mainly by advanced user or service engineers. And here, the instrument can be calibrated using a fresh control blood or a fresh human blood with known values, or can directly adjust parameters calibration factor. So here provide a quite advanced or powerful tool to manually calibrate some parameters, but the user need to know the reason why these parameters need to be calibrated and what factor should use. So here it is an advanced user feature. And for the end user using guided calibration and calibrator blood, they can also independently calibrate the instrument. The QC menu provide the function for input assays. Each control blood lot has an assay sheet with 9 barcode. So here, user can input the new lot of the control blood or calibrator by input with a barcode scanner. The sample X bar using sample results, 3 major parameters which are quite stable for all samples: MCV, MCH, and MCHC. So these 3 parameters are quite stable for all human samples to long-term monitoring the instrument stability. And for control blood, it is a Levy-Jennings plot for each lot number of the controls, and many parameters are monitored. Service menu is very useful for troubleshooting and also to check the instrument status. And here we can do, for example, each component of instrument test, pump and valve test, and also to see if there is an environment interference noise from other instrument or from a bad grounding. The CVP menu, it is the place where we can adjust the gain of the WBC, RBC. HGB menu provide the setting for the LED light source and photocell in case user report age related H started error flags. The system info contains the serial number, IP address of instrument, and the technical parameter. There we can see very important parameters like the counting time for RBC, WBC, the aspiration time for whole blood, and the transfer time. And these parameters actually reflect the correct aspiration counting of these either a dilution step or the measuring steps. The normal range for the counting is quite fixed. For example, RBC is about 13 to 16 seconds. For WBC, 9 to 13 seconds. And if the counting time deviates, either could be a capillary aperture clogging, or the pump to provide the pressure could deviate, or the valves, the loop of tubing after the aperture has higher resistance. So these parameters can give us some information regarding the status or the healthy of the instrument. I think I'm quite near the end of my presentation, and before we close, I also like to bring up the important feature, which it is pretty simple, but there has some report related to the shutdown of instrument. Some database corruption message can appear when instrument was shut down during the night and restart in the morning. Database corruption appeared. Some corruption can be recovered without any change of a database, but some database is lost. Sample results and reagent control blood entries disappeared. But in worst case, database corruption cannot be recovered and the user cannot reach the main menu. So, and we find by analyze the technical files, we find some connection between the sudden power down of instrument and the database corruption. So this is why we like to bring up this topic in case the end user shut down the instrument often. The only correct way to power off instrument is by go to maintenance menu using power down button, and instrument may give some warning message. After confirm the user like to power down, then a message show up. Wait 10 seconds after display goes blank. So user really need to see the screen turns black and wait 10 seconds and then switch off. It is pretty simple and pretty obvious, but some case the instrument technical files indicate the instrument was powered off suddenly during the instrument, the database is still open. So we like to put some extra emphasis on this. So this is what we like to give you as an introduction for Medonic M32. I hope this webinar gave you some structure how to present the system to the potential user, and also how to think in a structured way to answer the user questions. And here we like to also see if you have some questions regarding this webinar. We will collect the question and get back in 1 minute.
Hello, everybody, again. I was just thinking while you're preparing your questions, if you could send us a comment or even like a question, how many persons you are sitting in the room watching this webinar. It's interesting for us to get that kind of information. If you're only 1 or 2, maybe it's not necessary to write, but if you're a number of persons, please write it in a comment for us so we will understand more who we are talking to. Thank you very much. Be right back.